Hello, everybody. My name's Quentin Stafford Fraser. I am delighted to welcome you here to this event in memory of and in celebration of the work of Dr. Alexander G. Fraser, known to most of us as Sandy. We've got some great speakers lined up here. I think it's going to be a fabulous event, and we're holding it slightly later than usual on our Wednesday afternoon sessions because we knew people would probably want to join us from the other side of the Atlantic, where Sandy, of course, spent most of his career. So welcome to everybody who's joining us on the recordings or live now. It's great to have you with us. We're also delighted to have Elizabeth and Tim and Phil Fraser here. We'll be hearing a little from Elizabeth later. She is, of course, a Cambridge alumna herself, having taken the diploma in was it numerical analysis or was it computer science by the time you took it? It was numerical analysis and automatic computing, right. So Elizabeth is a graduate of what was probably the world's first proper full-time computer science degree. Don't want to make you feel old. Now, I'm no spring chicken myself, but Sandy was working on computers in Cambridge well before I was even born. And one of the key things he worked on as part of his PhD here was the file system for the Titan computer. Now, this was interesting because the Titan, in addition to usual tape drives, also had two hard disks. Oh, no, wait, that's not a hard disk. This is a hard disk. Now, this is one of the platters from one of the hard disks in the Titan, and we were trying to work this out earlier. We think this probably holds...
I just realised the Zoom, for some reason, the Zoom video isn't showing.
So we don't see them. There you go. Now, can everybody see me? Right, this is a hard disk. Okay, so this is... we think this holds about 5 to 10 megabytes, something like that. It's a little uncertain because the standard of an 8-bit byte wasn't really established then. But this is fairly heavy. To give you an idea, if I had about 2,000 of these, I would have considerably less storage than I currently have on my watch. But I like to think, in the very unlikely event that there's any data still stored on here, that it's in a format that Sandy designed. So this was cutting-edge computer science technology when Sandy started in Cambridge. And when he returned many decades later, and when I first knew him and worked with him, we had mobile phones in our pockets, and we had digital cameras in our bags. And of course, Sandy went on to do important work for many, many years after that. And so his career spanned almost the entirety of what we think of as modern computer science. And today we're going to hear from people, from Cambridge people who worked with him at various key points during that long and influential career. And because of the format we have of lots of short talks here, I think it's going to be easiest to try and keep questions until the end. So if you are joining us remotely, we will try and collate them on Zoom and ask them for you at the end. Don't worry if they vanish from the Q&A section. We will have noted them. And afterwards, there are refreshments as well, so you can ask questions of the speaker then. So now, I think there's no better way to start than to hand over to David Hartley. I'll let him introduce himself, but if you could join me, please, in welcoming him. Thank you.
Fine. Yep, that's that. Good. Thank you very much. If I fall over, don't all rush to help me up. I've got a stick here to do it for me. I got the Morris Wilks bug. I go around with a walking stick. So, I really need to talk about Sandy when he was here, back in the 1960s. And I'm going to talk actually a bit more wider than that. I'm going to talk about the first era of computing in Cambridge from 1937 back to 1970. And you'll see why in a moment. I need my glasses on. All right, I'll do without it. Okay. So we start off with the early years in the computer lab. It actually wasn't the computer lab, it was a mathematical laboratory. And I shall call it the maths lab, as we all did in those days. The only people here today who were there in that period, there are three of us, I think. If I've missed somebody out, please tell me afterwards. But Joyce Wheeler, who is there, wife of David Wheeler, of course, and Elizabeth herself, and me. We hope to have Barry Landy here, who was one of my colleagues on the Titan operating system, but he had to cry off at the last minute. While the Maths Lab was founded by the university, and it was founded as a place to encourage the use of computation in science. Because in those days, that's what they used, Brunswickers. But electronics were sort of coming, and someone had the foresight to say, new technology is coming, and it's going to be an important business. Not only to build the darn things, or get them, but also to encourage people to use them. So the Maths Lab was founded, I can make this work, wrong one. I'll get it right in a minute. You said it was this one, didn't you?
It's slow. Oh, really?
That's right, don't go too fast.
I was just checking it was working. Yeah.
That's okay. So we were the Maths Lab was founded in 1937. That's the building it was in. Used to be an anatomy lecture department. And I've gone the wrong way around now. There we are. Its first director was Professor Leonard Jones. He was very much into computation, but he was actually in the chemistry department. And then he had one academic member of staff, and that was Maurice Wilkes. He came there from physics. But no sooner had they got going that the World War II came and it intervened, and as a result, they all went off. The lab was closed, and everyone went off to do war service. Maurice came back, and he found that he had been appointed acting director because Leonard Jones was still in the war. And he had two complementary ambitions. And this is my way of putting it. He had a mission. The mission was to develop facilities from new technology, i.e. to build a computer. But it wasn't known what would be done. It was a blank sheet of paper. He also had a vision, did Maurice. He wanted to provide a service to all scientists and others in the university to help them with their research, to help them do their computations, because doing it on a Brunswicker was hell. It got going. The EDSAC was built and came into service in about 1991. It was a miracle it worked. We know that because we're building a replica at the moment at Bletchley Park, and after 10 years it still doesn't work. Anyway, Maurice founded a course in computing. It was one of the first in the world, and it was called the Diploma in Numerical Analysis and Automatic Computing, as you heard a moment ago. And it began in 1953. It was a refuge for those who wanted to change into computing. It's a one-year course. And the students in 1958-59 were two people, well, more than two, but two particularly, Sandy Fraser and myself. Sandy was at Bristol University. He did a course in aeronautical engineering at Bristol. I was privileged for Elizabeth to show me his thesis that he wrote. It's quite clear to me that he wanted to change. Well, who wouldn't in aeronautical engineering, even in those days? and he wanted to get into computing somehow. Myself, I was a bit of a failure. I was here in Cambridge reading the mathematical tripos for 2 years, and after 2 years, I just couldn't do it. It was just too darn difficult. Anyone here who's done the mathematical tripos, you probably know what I mean. We both did this course because we both wanted to change subject. And we were both awarded distinctions. 5 out of the 12 students that year got distinctions, and Sandy's and mine were 2 of them. We're rather pleased by that. So, EDSAC 2 was replaced. EDSAC was replaced by EDSAC 2, and it began to work in 1958, and it went until 1965. It was a dream machine in many ways of David Wheeler, and there is a picture also of the job queue. The users lining up to put their paper tapes in the machine and take their turn to test their programs. It was a brilliant design by David, it really was. And I'm sorry that he's never been written up, in my opinion, for the public. EDSAC's been written up all the time, but not EDSAC 2. We didn't write it up because we're too busy doing other things. And certainly David never wrote it up anyway, as Joyce knows. It was better in terms of speed, its functions, its storage capacity, and its reliability above all. It did work, and it worked pretty well. It had to be attended by the engineers every morning to make sure it was all right, and check a few things from time to time, but that was marvellous concern with EDSAC. It was a wonder in any one day that EDSAC kept working all day. And it was a dream for the users. It was easy to program, and what it really did was it encouraged computing to happen in Cambridge, because it was so much easier than EDSAC. And that's really all part of Morris's vision, to encourage the use of computers. Then, in 1963, we started the Titan project to replace EDSAC 2. EDSAC 2 was going to exist till 1965, we decided, and we persuaded Ferranti, or they persuaded us, I don't know, to build a cut-down version of their Atlas computer, which was really one of the first supercomputers around. It was extremely expensive. We couldn't afford one. We couldn't get the government to give us money for it anyway. And so, in the end, Peter Hall, who was the head of computing at Ferranti, made a very generous thing to us. He said, we will build you a cut-down version of Atlas, just the CPU, and not much else, a bit of storage, the odd few manual tapes, and the rest you can do yourself. And in particular, you have to write the software, because the software for Atlas was so odd, if you like, in a way. It's one-level store and everything. And so we had a big task on. The machine arrived in about 1965, or 4 or 5, I think, and it was really there for us writing in the programs to test them out. But it was a big job. We really had bitten off more than we could chew, because the operating system in those days was going to be much cleverer. EDSAC 2 didn't have an operating system. He just took one program at a time, the users put them in, took the results away, looked for their errors, and came back, and then someone else did it. But the Titan, Atlas and Atlas 2 and the project were to do much more fancy things by time sharing the CPU between different jobs at the same time. And we therefore were faced with the job of having a different computer architecture to do the same job on that Manchester were doing. So we had collaboration with Ferranti, an ambitious software project led by David Barron, and then it got a bit late, and the machine was there. We were testing programs like mad, but there was no service. And users got rather cross about that. Fair enough. We spent all that money on it. Anyway, it was endowed eventually with a temporary operating system and temporary compilers by Peter Swindon Dyer. I suspect no one here knows Swindon Dyer except those who are the two ladies. Ken does as well. He was a fantastic programmer. He broke all the rules. He would sit down and think out what his software was going to do, a whole operating system, worked it out in his head. Then he wrote it down, what it was going to do, and then he wrote the program, usually in pencil, on a piece of paper. Lots and lots of code. And that was it. And then he'd give it to someone else to test it, and it would usually work. A few bugs were found, not very many. It was incredible. I mean, he broke all the rules of programming of those days, and probably now. But he was like that, and he saved us, in a sense, by creating a temporary operating system and a temporary service. What we were really trying to do was write the Titan operating system, the main system. And David Barron, who was leading us, moved on, or moved away, to run the temporary service, and Roger Needham took over leading the team. The team was led by him, plus myself, Barry Landy, who can't be here, and Mike Guy, who we don't know where he's got to. Morris was a regular visitor to MIT, and every summer he would go out there and refresh himself and find out what was new there. And he discovered one year, in fact it was 1965, that they had done time sharing. They had developed a system where people sat at terminals, lots of people sat at the same time at terminals, and had a business machine to use. And in other words, instead of having one machine, we really had several machines. And it was remarkable. And that was the wonder of the age. And shortly after that, everyone wanted to write a time-sharing system. Now, Morris came back from MIT saying, we've got to do time-sharing. We've got to stop what we're doing, rewrite what we've done, and do a time-sharing system. It was a big step. And everyone he talked to about it in the lab and in the university said, what a great idea, you should do it. And except Roger and his team. And we were didn't really like that idea. We were too busy writing the damn thing, and we looked like all our work was being undone. And then Morris had a bright idea, or well, he had a windfall almost. This young man, Fraser, had come to the lab and had asked for a job. Now, actually, Sandy had been before in the system because he'd been a diploma student. And he had a distinction, so why should he refuse? He was a graduate and a good graduate. So he took him on. In fact, Morris was all very good at finding temporary money, and he used that to employ Sandy. And Sandy joined the team to write the file store. There's one job we hadn't done. Everything else we were busy with all the time, but we really kept leaving the file store aside. And Sandy joined the team to develop this file store. The time-sharing system was then eventually converted. It was a long sweat, but it opened in 1967. And it opened with a big bang, because everyone liked it. It did work, fortunately. They wouldn't have liked it otherwise. And suddenly we had a good system, almost overnight. I won't tell you the story of the party we had on that day when it started working, but it was right a boozy one. And Morris wasn't invited. So this was an end of an era, because Titan kept going on now to about 1971. And time-sharing made Titan a big success. And instead of the users in the university and I'm talking about the big people now, the professors and so on, who have been moaning about the computing service was no good and so on, they all said, my God, that's good. You've done well. You're a bit late, but there you are. And so it then coincided with the need of the university to do a formal review of the computing service and the laboratories altogether, maths labs as well. And from 1970, essentially we're going from the old era to the new era. The old era was very successful. I hope by what I've said, I've told you he's done an enormous amount of things, and particularly in respect to Morris's mission and his vision. And we went from having no computing to talk of, to computers that didn't work, and then to computers that did work, then computers which were bigger and a good size. David Wheeler's programming language for EDSAC 2 was indeed the wonder of the age. I remember in preparation for this lecture, Elizabeth found Sandy's old thesis for the diploma, and it was full of EDSAC 2 programs. It was beautiful. I don't tell you why it was beautiful, because you wouldn't know, you wouldn't understand. But I thought, gosh, I remember those days. So we became two departments. Computer science research and teaching was one half, the other half was the computing service. And although Maurice was still in charge overall of the department, we had a director of the computing service, which happened to be me. We were separated from the mathematics faculty. There's no need for that. We were independent of them, any faculty, and we would become the computer laboratory. And of course, that's the name it's still used by most of you here today. You still call it the computer lab. I'm glad you do, because the actual formal title is a bit of a mouthful. So undoubtedly, 1970 was the end of the first great era of computing in Cambridge, and it was the beginning of the next. The lab has been faithful to the mission and vision, and here are two examples of what we've done since then. Of course, computer science in Cambridge, I don't need to mention, has become worldwide and world famous, and I don't need to talk about that. You know, that's you lot. And but the computing service did a number of things which I would count as part of fulfilling Maurice's vision. I'm going to give you two examples here. The Titan time-sharing system had a particular language and particular features and a file store and so on. And we then moved to IBM mainframes, which had terrible software. Anyone old enough will know that. And IBM could never write, and big computers, big companies can't write good systems. And so we rewrote a version of the time-sharing system and put it on the IBM mainframe. This is in the early 70s. And that system lasted with thousands of users, very happily using Phoenix, as it was called, right until the middle of the 1990s. And that was really quite an achievement. It's now out of date, that achievement, of course. That doesn't matter. It had moved things forward. And it moved forward in particular that vision of having more and more users being helped by computation. Then there's this thing called the backbone network, which was implemented in 1992. One of the things we realized that users wanted was communications back in the 70s and 80s. And so that they could talk to each other, they could send information to each other and so on. And it was we saw in the 80s that it was going to be a big demand for more and more bandwidth, as the whole world now knows that. We persuaded the university and 31 separate colleges to fund a network of ducting under the roads of Cambridge with fibre optic cables in them. That was quite an achievement. It only cost £3 million, but in 1989, whenever we started it, it was a lot of money. But I persuaded somehow the university to do it. I had a terrible meeting. I had to meet all the bigwigs of the university, all the members of the big committees, all the professors, all the bursars, into one meeting in the Cockcroft Lecture Theatre, where I made the case for this funding. It had been generally approved all around the university, but the university treasurer decided he wasn't happy. And so one of the senior administrators of the university said, well, we'll have a meeting. We'll have a meeting of all these people and you will address them. I had the Vice-Chancellor in the chair, and I stood up in a lecture theatre like this and made my case. There were one or two people who grumbled a bit, but they're not just as complimentary as I think they should have been. But as the meeting broke up, the Vice-Chancellor said to me, "Don't worry," he said, "it'll happen." So I felt happy. And so we did that, Rob. That's it. We think it's quite a marvel. We apologise to London Transport, but that's a map of our network in Cambridge. That's the data centre down there on the bottom left-hand side, and all the places on there are buildings of the university or colleges, and it stretches throughout the university from Girton College in the north and Adam Brooks in the south. Since then, it's been extended. This was in 1992, would you believe? And that was, enough. So, I can give you my tribute to that team. This is a quote from Roger Needham, a typical Roger quote. I loved it. "It was fun if you're in our trade. Nothing gives you gives you a charge like having put together a system which nobody else can match." Typical Roger. And also Sandy. He came and he helped us out in quite a big way, and we're very grateful for that. So thank you, Sandy, for all your help, and I hope you understand and agree that back in the 60s, we didn't do a bad job. And Sandy helped us a lot. Thank you very much.
Thank you very much.
Okay, now it's on. Okay. So today I'm going to talk a little bit about Sandy's contributions, not to computing, but to communication, because he is actually very well remembered and very well known for his communications. And so I'm going to try and give you a very brief tutorial on the technology of what he did. If I can get this to move forward. It is... okay, yeah, there you go. So I'm going to talk a little bit about the technical contributions. Sandy is an organization man. He was actually at the top of a very large organization, Bell Labs, and some personal notes. So I want to start with this paper that came out in 1983, which talks about the work he did in November 1969 in something called asynchronous time division networks. And it's a mouthful. You don't need to understand it. But what I want to draw attention to is this picture over here, which is actually a hand-drawn picture from his paper from 1969. It's a Bell Labs technical memorandum. And what you see over here is actually something fairly straightforward, if this pointer works. So over here, we have packets coming in, data coming in, and this way data is going out. So this is what's called a crossbar switch. And what he invented was a way for data to come in and sit over here in a queue for a while and then go out again. And so, so you didn't have everything synchronous. It was called asynchronous. So that was the fundamental innovation that came out in 1969. And he added to it something else called virtual circuit switching. And this figure, you just need to remember one thing about the figure. It's got A, B, and C. And I'm going to explain all of it in the next slide. So that's all you need to know. It's got A, B, and C. So let's see what it actually means. Let's call a letter like this L. We'll call that L just to not draw letters all the time. Let's call a post office P, right? L is a letter, P is a post office. And a letter arrives to a post office, and they have to make a decision. Either it's local or it's remote. So what do? You look at the address and you say, this address looks local, let's deliver it. This address looks not local, let's give it to somebody else to deal with it. And that's called the routing problem. What if you have lots and lots of letters, all the same destination? You have to read the address over and over and over again. That's kind of painful. We'll just tell them, just put the number 1 on it. When I see the number 1, I mean, I know what the destination is. I've allocated you the number 1. And when you see that, I'm just going to pass it off to the remote location because I know number 1 it is, and I don't need to read the whole address, which could be very long. And so this idea this number is called a virtual circuit identifier, or VCI, but there is a problem. What if one is already being used? So this post office over here says, I gave one to somebody else. You can't do that. No problem. We'll take care of that. We'll just add a translation. When something comes in with 1, we're going to remove that 1 and stick on it 26. And 26 is something that this remote one isn't using. We check that in advance. And when we do that, we can actually set up a system where when something comes in over and over and over again, millions of times a second perhaps, we don't need to look up long, complicated addresses. We just look up numbers, small numbers, and we translate them to other numbers. And for that, we need a table. And the table says, if something comes in with this number, send it out to the remote port and call it 26. And this is called a translation table. Make sense? Good. I was hoping that, that he would understand it. Okay. Now, what we've done is we have created this network with this bit of translation in it, and this fundamental idea of trying to map inputs to outputs once by a control processor, which looks at the addresses and replacing it with small numbers, which can be done on the fly, makes it possible to build very fast, very cheap switches, which are called virtual circuit switches. And this innovation was what Sandy came up with in '69. So I'm taking over from 1970 when he went to the Bell Labs. The first thing he did was sort of invent this, draw that little bit of a picture, and build a series of networks which all incorporated this idea of virtual circuit identifiers. What if the arrivals are not letters, but frames from a movie? You can do something better. You can say, I'm setting up these identifiers anyway. Why don't I do one more thing? I'll also reserve a fraction of the link. I'll say, this is a movie that's going to take 10% of the link. I'm going to put that on the table. This quality of service, QoS, is 10% of the link. So the first movie comes in, you allocate it 10%. Next comes in 10%. When you full up, the 11th request comes in, you say, sorry, you can't take it. It's full up. And this way, the 10 existing connections will all get good quality of service, and the 11th one is denied. This is fundamental to how the telephone network works, and this is why the internet doesn't work, because we don't have this on the internet today. The internet, everybody can come in and nobody is denied. Everybody is denied in some sense. So we all get poor degrading. So you have often seen on BBC, there's an interview, oops, the sound quality was not but very good. We're on voice over IP. That's because they don't have these tables. So Sandy solved this in 1969. We still haven't caught up with him. There's some good reasons why. Imagine that this post office collapses. Something happens, that switch dies, and we're going to reroute the packet, the data from that is going to send over here, 26, we send it to 26 over there. Now what happens? This one says, I don't know what 26 is. Okay? So what we need to do is to reestablish the connection all the way to the destination, saying, by 26 I mean this, and this destination all over again. And if, let's say, 1 million connections are going through over here, all 1 million of them would need to be rerouted all at once, which puts a very big load on what's called signaling. And this means that this switch over here has got to be very, very reliable. It's going to be going down once every 100 years or something like that. And that makes the switches very expensive. And what the internet people decided to do was to make switches in a different way, where you actually look up the letter address each time. And this way, you don't have numbers anymore, you actually have the address. But every bit of gear needs to know how to read addresses and to forward them properly. So that's the fundamental trade-off. Either have expensive switches which maintain these translation tables, or have cheap ones, but they need to do a little bit more work. And the internet today is designed in a way which has these kinds of full addresses, not these identifiers. But setting that aside, this is basically Sandy's technical contribution, and it was a very fine one. So because the virtual circuit identifiers and the tables that go with them allow us to provide quality of service, which is how we would like to build networks today. And in some subsequent talks, we'll see how these ideas continue to live. And 2 existing services today are actually built on these ideas, that they come back with different names attached to them. But I'm going to just talk a little bit about the networks that Sandy built. One of them was called DataKit. This was not the first network he built. The first one he built was called Spider, but I couldn't find any pictures of these. But this is DataKit. This was built around 1973, 74. And remember A, B, and C? Well, it's back. He actually used the same figure as redrew it slightly differently. It's still A, B, and C, but still the same. And it's showing exactly what I said earlier. They're both sending the number 3, and he's sending them with 15 and 2 instead. And that's the translation table right there. 3 goes to 2, and this 3 goes to 15. And that's exactly the translation table. So now hopefully you understand what this figure means. And it's actually cut and paste exactly from the 1983 paper. That was DataKit. DataKit was quite successful. Many people use it, including me. But even more interesting was this thing called XUNet2, Experimental University Network 2, which was a testbed that Sandy set up. This is a paper that he wrote in 1991. And it was a collaboration between Bell Labs at one end and quite a few universities. So there was over here University of California, Berkeley, where he was a graduate student, and then Wisconsin, Illinois. And so these universities worked with Bell Labs. And my first summer internship in 1989 was as a graduate student in Bell Labs, working with Sandy on XUNet2. And in those days, grad students didn't have pinups. They had these instead. This is a picture of of the board over here. This is the XUNet board. It was a beautiful board, I have to say. And I worked on it quite a few years. I have some. I spent many late nights with it. I had a lot of fun. I won't tell you what we did, but anyway. So I wanted to switch to Sandy as an organization man. No, Sandy was not just an inventor, not just an innovator, but he was also an amazingly well-respected person at the top of a very high pyramid. So here is the pictorial directory from Bell Labs. This is actually all of Bell Labs. So they call it BL011, September 94. And here's Sandy from 1994. That's what he looked like. And this is what I looked like in 94. I'm also in this book. But here's to explain how this is. Here's all of research was broken up into these divisions. So 111, so physical sciences was 11. 112 is research, information sciences, and so on. 113 is communication. So Sandy was 112. So you can see right here, 1120. That means he was the executive director, and he had a whole bunch of people working for him. Just to explain who these people are, so everybody at Bell Labs went by their email ID. So this is Arno Penzias, who won the Nobel Prize for Physics, and Sandy reported to him. That's AGF. And then all these different computer departments, and this was 1127, was computing science. Ravi Sethi, who wrote the Dragon book, and Mihalis Yannakakis was a theoretician, and I was put in theory. But these are the people who also worked there, Ken Thompson and Dennis Ritchie, DMR, who invented Unix. There's some other people who are perhaps, I don't have time to talk much about. BS is Bjarne Strustrup, who did C++. And MJD is Joe Dixon, who was an undergrad from Cambridge, who spent a year working at Bell Labs. He was the first undergrad from Cambridge I had worked with, other than Sandy perhaps. And he gave me a very skewed view of what Cambridge undergrads were like. But the point I want to make here is that Sandy was on top of this very large herd of cats, and he herded them very well indeed. He was really universally respected, and we all sort of, anything he said was like, words of wisdom, pearls of wisdom. We treasured everything he said. I'll repeat some of them to you in a minute from now. And he also was organized about university research. He had the intuition, a very good intuition, that in order for his ideas to take root, it wasn't just good enough to publish papers. You need to actually create an organization that goes beyond Bell Labs, beyond AT&T. And he set up his consortium, if you will, a research consortium with Berkeley and Wisconsin, Illinois. And there's a whole generation of students my age who went through Bell Labs and were trained in networking with Sandy because he provided that vision of where things should be. And so, I'm really grateful to him, and there are many others who are from my era, so between 1989 and 1994, who worked with Sandy at the labs. And then he went off to AT&T Labs, that somebody else is going to pick up the story on. Just want to say a few things. The first thing was after my first summer internship, I was at Bell Labs, and at the last day there, Sandy called me to his office. I was dreading, what is he going to do to me? And he said, would you mind terribly if we would offer you funding? I mean, we don't need to give you a job. We will give you a job. You don't need to take it. We just want to offer you funding. Would you mind terribly? And I was like turning cartwheels, like, whoa, I don't have to worry about money anymore. But he's put it in such a gentle and nice way that I was absolutely delighted to say yes, and of course I was thrilled to get a job there with him. And then the first day on the job, he brings me to his office, he shows me, he says, I want you to work on something that will be relevant to AT&T 25 years from now. So this was in 91, so he wanted me to work on something relevant to AT&T in 2016, by which time AT&T had been dead 20 years. But he said, don't work on Egyptian hieroglyphics. And it turned out that somebody else at Bell Labs had been working on verifying eclipse predictions in Babylonian cuneiform tablets. And the AT&T thought that wasn't quite research for computer science. So there was why no. And then the last thing I want to say is that Sandy loved working with students. When I was a graduate student, he would organize picnics, and the one memory I still have is he took us all out to Lehigh University, where there was a racing going on in a velodrome, and he really loved bicycling. And he said, this is how proper cycling is done. So I still remember that. So I'm going to stop with that, but let me just end by saying it was just a great pleasure to have Sandy as a mentor, as a guide, as a teacher. I will always remember him with greatest of fondness. So thank you. Should I show this? Yeah. I want to say one last thing. Actually, what I wanted to say at the end. This is a sales invoice from a company called 4 Systems, and I thought I'd just show you something here. So 4 Systems was the ATM network, which is what Sandy invented, and R is Robert Sansom, and this was an invoice made out to me for an ATM computer interface, and Robert Sansom funded my chair, which is what brought me here. So in this invoice, everybody's all on one page. So anyway, thank you.
So let me say, I'm Andy Hopper, let me say a few words about how AT&T Labs, AT&T as a whole, came to Cambridge, this Cambridge. So in 1999, AT&T purchased Olivetti Research Limited, which was an independent 50-person or so research entity. The lab was for sale, and there were 3 suitors. Sun, Oracle, who were partially funding the lab, that industrial lab, and AT&T. Riches beyond belief. So what happens? Sandy, actually Elizabeth in some ways. Many interactions. Sandy convinced both AT&T to make the purchase, first AT&T lab outside the US, convinced us, and I mentioned Elizabeth because we had dinners, which you were included on, which discussed what might be. We were very jealous of our method, and there we go. And so I guess Sandy also convinced us, some of us are here. And so in 1999, Olivetti Research became AT&T Labs Cambridge Limited. Okay? And so Sandy, just as Keshav said, had the experience, the nous, the savvy, the trust, the everything to make sure that the culture that we had, that Cambridge has, that the computer lab had, was not perturbed by this gorilla called AT&T in the US. And this is not a straightforward task. You've got to be pretty influential up the AT&T line, as you would understand. So he was able to do that. So first of all, we continued as a limited separate company. I was the managing director, and the processes were all local, not the big gorillas ones from remote. That took some doing. I take my hat off to him. And in particular, the board of directors consisted of the UK company, of Sandy himself, and then he arranged, again, know that by all his charming skills, to have the Vice President Research, Larry Rabiner, on that board, the COO of AT&T, Dori Yokum, on that board, and one independent, which actually at the time was quite difficult, was Herman Hauser. But the idea of this independent who is a venture capitalist, oh gosh, that must have taken some doing, because from an AT&T perspective, he's going to rip everything off and AT&T ain't going to get nothing, right? So that was his great skills. And the purchase was because of the Cambridge cluster, the importance of our cluster, where the computer lab is, of course, pivotal in every way, but the other companies, not least the ones spun out of what became AT&T Research. And so I well remember him looking after us in a number of ways, not least this bellhead approach about virtual circuits and nailing things up, and many, many conversations. It's almost like a fireside chat. The lab would gather, the master would speak, and we would pick it up. And it was different to our local culture in a technical sense. And so that was a fantastic influence he had, which was very, very easy to take on board. But he was a corporate man, so, playing that game, right? So within a month or two, the CEO of AT&T, the big guy, came by helicopter to the airport, came and visited us. You will understand within large companies, such things help budgets and things like that. So there we go. So it was absolutely marvelous for him to be able to achieve this, and we doff our caps to him. But there are three things which I'll finish on, which are kind of consequential. Number one, AT&T hit quite a serious buffer and made a lot of redundancies, decided to shut us, but also made redundant, as we'd say in the UK, all that board, so that the protective layer also all disappeared, right? So it was quite a thing. So what he had set up was no longer available. But from that came Fraser Research, and so his work and his existence continued. But the final note I'd like to say is just to comment how implicated he was in one of the worst commercial misses in the universe. In fact, the worst one. Okay, so here is the story. He comes along, says, virtual circuits, quality of service, you got to set it right, you got to manage it, you got to be lightweight, all that sort of stuff. We said, very good, very good. So he says, what are you going to do? Well, we thought, what should we do? AT&T will design a better telephone system, or better telephone. Sounds like a good idea for AT&T. You'll remember people working on the project. So we designed such a thing, and if you were to look at the user interface, it had what we call snacks, which are little things you could press, and what are now called apps would start happening. And the number of pixels per each one of these things is exactly what's on the iPhone. So we had a prototype of what is now the iPhone. And so if you're going to miss, I believe the iPhone and its ecosystem is the most profitable product ever of any kind. So I'm very pleased to say that Sandy is implicated and his influence had an effect on a miss, which wasn't his fault, of the world's most profitable product ever. And we miss him a lot, so it's very nice to point that out. I think everybody
Okay, so I'm Alistair Beresford, and I work here in the department. But I also spent some time working with Sandy on 2 occasions too. So in about 2000, I was working at BT Research Labs and I decided I wanted to come back and do a PhD. And I had a good conversation with Andy Hopper and found funding, and I started. And around that time, AT&T had just invested and bought the local research lab. And so Sandy was over in one of his trips, and we had a great conversation about networking and so on. And I was lucky enough to be invited to do an internship in the summer of 2001 with Sandy in the Shannon Labs, or AT&T Labs Research in the US. And this is a photo from the time, and I'm not normally one for taking photos, but I bought a brand new digital camera, my first digital camera that summer, so there happens to be a few pictures that I can use. So this is what the networking looked like in 2001. So on the right-hand side, you can see a picture of a sort of a modem or a device we'd install in a house, and then what the local networking would look like between houses and a central office. And Sandy's great vision was due to the fact that AT&T had been buying up cable network companies in the US. Should we think about perhaps replacing the networking technologies used by those cable companies with something modern, supporting full computer networking? And so as part of that vision, I came over the summer of 2001 to work on this project. And my job was to look at how to deal with local routing across this last mile between the central office and homes. And so on the table, you can see there are 6 switches. And the idea was that we would be able to plug in, as the phone engineers, cables in arbitrary places, and we'd automatically work out the topology and work out routes for these virtual circuits that would route the data reliably through the network. And the executives loved the demo because they could walk up to the table, plug and unplug all the networks, and see on a television next to it live television being broadcast through to the television screen, and also see the topology being calculated as well. And I had a wonderful summer working with many people there. So wonderful that in 2004 I went to work with Sandy again, this time when he'd formed Fraser Research in Princeton, and again working on networking. And once again, a wonderful time, this time looking at naming of systems and services on these kinds of networks, focusing on making them secure and privacy aware. And I was reflecting, thinking about giving this talk, what are the properties or the things that I've learned most from Sandy that have lasted in my career as a researcher since? And I've tried to narrow it down to 3. So the first is think big. And by think big, I mean think of a large-scale project and a problem that you really want to solve that you think is going to be really important to society. And in the networking project, think big meant, there are 100 million homes in the US. How do we get 100 megabits to every single one of them? And if that's not big, I don't know what is. And that sort of idea of thinking about doing long-term research that's going to be significantly impactful has stayed with me. The second one is about communicate clearly. So Sandy really loved demos, as you can appreciate from all the things we've heard today. And the train set demo for plugging and unplugging all the switches was fantastic for that. There's another one that I really love from my time in the US where I'm working with another researcher, Andy Warfield. Sandy came to us one day and says, I want you to try and make the internet look really fast. And I'm like, what do you mean? We can put the internet over this network already and it works and everything. And he says, well, the problem is the web pages take 5, 10, 15 seconds to load, and that's terrible. And I was sort of just used to the internet being like this and websites being relatively slow. Anyway, we went away and thought about it, and basically we realized that if we were to take screenshots of a web page that once they'd been loaded, and remember where on the screenshot the links were, we could then crawl a website and build a sequence of images representing the website. And when you clicked in the right place on the image, we'd load the next relevant image for the user. And given this was around 2001, most websites were sort of like documents, and this worked surprisingly well, really impressively well. And I thought is this idea really going to work? But it felt like you were about to click the mouse and it already loaded the page. It was really stunning as a demo. So making demos and thinking about how to communicate clearly was another thing that Sandy really impressed upon me. And the third one is community. As we've already heard today, he was very good at supporting and helping build large research projects. And I was really, particularly in 2001, blown away with the setup that he'd arranged for AT&T Labs in the US. The breakout spaces and the comfy sofas, the quiet offices, and the multitude of social activities that happened in that lab were really fantastic. Unfortunately, I don't have lots of photos of that, but I do have one photo of us playing volleyball in 2001, just as a taster of some of the things that we organised while we spent our time there. Okay, I'll hand over to Glenford.
Okay, I'm Glenford Mapp. I used to work with Sandy at his time at AT&T. So people talked about Sandy being a big thinker. So this was the project brief that Sandy landed me with. How do you design a system that's going to work for the next 100 years? So this was the initial thing. It was to encompass all forms of communication. At the time, people were thinking about IPv6, but it had sort of fallen away, but Sandy was keen on the project. So that was it. So this is what we thought about, but actually it then came down to practical stuff. So one of the good things about Sandy is that Sandy could have these big visions, but actually at the end of the day, he liked to see something that worked. So you had to sort of boil the project down to something he could demonstrate to somebody. So this sort of project sort of ended up being sort of two practical projects. One would be internet radio, and it was run by Matthias and others. And the other one was what we would call today IPTV. So this is TV over the internet, but done in sort of Sandy's way. So Jim Snyder and myself, we were managed by Ed Chen, who was at the time one of Sandy's right-hand men. But at this time, these were groundbreaking projects because people didn't think that way. Okay, so I worked on the IPTV project, and the big idea was again to try and use Sandy's virtual circuits, but in a different way. So you would use IP as the signaling mechanism. So the whole idea is that when you wanted to talk to somebody at the other end, what you would do is that you would reserve 2 bits in the toss field of an IPv4 header. The first bit would say, I am capable of doing Ethernet virtual circuit. So it's just a capability. The second bit would say, I would like an Ethernet virtual circuit set up for this particular connection. So that's what would happen. So this ended up to be very flexible because, of course, if the destination or the intermediate router didn't know anything about Ethernet virtual circuits, it would just do a normal IP. So you wouldn't know any different. So it didn't affect what you had to do in the internet at all. And if the system supported Ethernet virtual circuits, you would get this very low latency connection, and that was great for audio and video, which is what Sandy was about. So he was really keen on this. So this is the idea. So your red is the IP packet. So the first packet of the connection goes across, and when it hits the other machine would say, okay, yeah, I'll do an EVC as well, and the EVC connections would go back onto this. So that's a blue. The nice thing about this is that you didn't have to do any big reservation going forward. You did all the reservation of the resources going backward. And that was really, really efficient. That was great. So these are the 2 switches that we built. You can see the one on the right is called Cambridge, because that's the one we had here at AT&T Labs, and the other one we had at Florham Park. So we did get a prototype working. We had to discontinue it quite soon after because, of course, AT&T Labs closed down. The project, though, pointed to the need to make flows first-class communication objects. Some of the things that Keshav was saying does come about here. And Sandy was very keen that idea be promoted. So he was quite keen on IPv6 and all the flow label stuff that that we still talk about today. This project, though, involved a lot of kernel hacking. And at the time, Linux, you could have done that with Linux because it wasn't that bloated. You couldn't do that today, okay? But interestingly, today, you could do most of this using SDN. So SDN technology sort of allows this to happen in a very sort of elegant way. But this project sort of predated SDN by a few years, but you could see the sort of thinking coming from this kind of project. Okay, some observations about Sandy at AT&T. My view is Sandy was correct to go to America and join AT&T, okay? There was a great synergy between Sandy's abilities and research at AT&T. And Sandy loved working with academia, but he himself couldn't be an academic. He would just be too bored. This is somebody who was always active, always doing stuff. So I couldn't see him as an academic. I don't think he would have been an academic. He admired AT&T, and I think that's true. And he admired AT&T for several reasons. But one of the main reasons he admired AT&T is that he always said that the smartest thing that AT&T ever did was to define the telephone service in terms of the electromagnetic spectrum of the signal. The service was not defined in terms of a particular technology. And Sandy always said that was the smartest thing they ever did. And he's correct, because that allowed different technologies to be used. And that's what happened. So we went circuits and TDM, all of that sort of stuff, drove through the telephone, AT&T, because of that initial definition. And Sandy thrived in that environment. Sandy loved this sort of thing because actually it allowed him to play games, to have fun. And that was Sandy. Okay, so it was brilliant. I mean, he in a sense, AT&T made Sandy, but Sandy also made AT&T. All right, Sandy the man. Sandy was not afraid to think differently. If you're in a room with 10 people and 9 people say, we like X and Sandy liked Y, Sandy would say he liked Y. Full stop. He was not afraid to be different. But also he was not afraid to be wrong. Okay, if he really believed something and you did not, you could show actually Sandy this wasn't going to work, it wasn't going to work. You would have to be very careful in how you convinced him of that. So we would say today, data-driven is good. If you want to convince Sandy of something, you've got to get the data, okay? But he really was good that way. The third thing I would say is that he believed in building things, not just as a way. He believed in building things to fully understand it. He didn't just believe in building things to demonstrate. I mean, a lot of people think he built things to demonstrate it. That's true. But he actually built stuff to really understand it. He felt that for you to really understand something, you had to build it. You had to build it. And that's true, I think, that came through. I would always remember him as that fourth point. He saw the internet would become the multi-service network we have today. And I think he saw it before most people. And I think that is his main legacy in my mind. He saw the multi-service nature of networking. And for that alone, I think he is probably one of our greatest pioneers. So thank you, and thank him, basically.
Go for it. Are you in the Zoom? Switch this one. So my story begins in 2002. And in about 2002, I had just joined Cambridge as a first-year PhD student, and my supervisor had given me a huge amount of work to do. And I had my own ideas of what I wanted to work on, and they were quite distinct from my supervisor. So I did what any self-respecting... Something's going on here. Let me just figure out what's going on.
That's all right, it was us.
That's all right. Okay, everything's good. My booming voice was not one of those things. And so I was hiding from my supervisor, and the perfect hiding place was Andy Hopper's group, so away from the systems group, and he's on the second floor, and it's a lovely place where no one could find me from the systems group. And I found my friend Dave, and it was one Sunday afternoon, and we were sitting in...
Sorry, the mic's not working on Zoom.
So I'm not sure why we've changed the microphone. Let's do a sound check.
If you change the message to are we only going these slides?
All right, let me see if I'm going to deafen you all. No? Are we good? Yeah, excellent. Thank you. And so we were sitting upstairs in the LCE, and it was a Sunday afternoon, and Andy Hopper walks past with this important-looking person, Sandy Fraser, and he walks past, and he suddenly stops, and he peers into the office, and he notices the two of us trying to be as quiet as mouses. And he noticed that we were using Macs. And back in those days, Macintoshes were very newfangled machines. They're just a new Titanium G4 had just been released, and I happened to have one of them. And it kind of got his interest. And he came and talked to us, and he perched on the desk. And before we knew it, we'd been interviewed. He'd explained what he's been working on. He just retired and was building an ambitious new laboratory in Princeton. And we just were chatting away friendlily. And before we knew it, Elizabeth had gotten involved, and we had J1 visas to the US, and we were shipped off to Princeton. And our plans for a quiet life of a PhD were shattered. But it did begin one of the greatest adventures that has influenced the way that we think about systems research and networking research ever since then. And the project that Sandy explained was this idea of the 100 by 100 network, the one that the project that would try to bring really, really fast broadband to 100 million homes in the United States. And remember, the backdrop here is that we were still using modems to connect, so we'd have to ask our parents when I was living at home to put the phone down, and then we'd have to put up a software modem, and you'd dial up around 56 kilobytes, and you'd try to have a good connection. So then 100 megabits ubiquitously across the whole country was an incredible dream. And the question really was how we could get there in such a way that we'd provide equitable access as a public network, maintaining the quality of service guarantees that would mean that everyone would get a reasonable experience. And as Keshav pointed out, we had all the atoms in place. We'd had things like virtual circuits. We'd had the ability to connect all these affordances together, but somehow people were still using layers over the telephone network instead of building a for-purpose system to do that. And so Sandy's vision was this idea of joining this big NSF project, the National Science Foundation in the US, to build this architecture. So the question that he's asking was, what should a next-generation network look like if combined with the learnings from the previous decades of these telephone networks? And by this point, Sandy had retired, so he was trying to start from a clean slate and not be too dragged behind by some of the various decisions made at AT&T Labs Research. And the key observation that Keshav made here is that we're asking if we can maintain end-to-end service quality, and as you've seen from just messing around with all of these systems and Zoom and so on, we still don't really have the ability to say, if we do something over the internet, can we maintain an end-to-end service guarantee that will be as predictable and as robust as relative as possible? So we're still not quite there yet. And the vehicle for this was Fraser Research. And Sandy had retired. Sandy and Elizabeth were now running Fraser Research as a not-for-profit company in the US in Princeton. And the vehicle for answering all these cliche questions were a set of interns gathered from all over the world. And Dave and I were the first two. But then over the years, many, many more of them came along. Put your hands up here if you were an intern. I see Simon is there, Stephen is there, Ali Beresford is there. All gone on to great careers afterwards. I'm still here in the computer lab, and I guess Ali is as well. But the interns were pulled in from a diverse set of institutions from all over the place. And the way that we worked with Sandy was kind of unique. This was a bit like a biologist suddenly getting to hang out, having fireside chats with Charles Darwin. He would give us stories on 1 minute about how he'd been negotiating bilateral agreements with nuclear powers about installing telephone connections, because they're basically electrical wires across international boundaries. And then the next moment he'd be deep diving into the specifics of an encoding for tables in virtual circuits in order to have a more efficient encoding mechanism. So there wasn't a bit of the software stack that would escape him, and we also were hungry to learn more. So we were having lots and lots of interactive conversations at a sweet shop called Thomas Sweet quite often, which is Princeton is full of these amazing chocolate shops. I highly recommend it even now if you go there. The Halo Pub, Thomas Sweet, and so on. And we'd hang out there. He had a great love of cycling. We'd go out to velodromes and hang out as Keisha mentioned, and also just generally taking advantage of the fact that we were in Princeton. And so when we went from this internship, every one of us had different projects to work on. So Alistair mentioned the idea of the fast web browser project. Can you just get to less than a few milliseconds in terms of how you click on things so that you have immediate response time, so it feels like you're running in a fast system? Can we extend Ethernet to be backwards compatible, a bit like Glenford mentioned, except instead of using IP packets, we try to extend switches themselves to work at a low level. And then all the way up to big ticket questions like how many telephone poles would you need to add into the United States so that every single home could have at least 2 wires going out of it, so that if one of the poles collapsed, a whole set of houses would still have connectivity. So asking the bigger questions around reliability as well as the low-level questions behind it. Now, I'm going to hand over to my colleague David, who's going to talk about one of the specific projects that we worked on.
Yeah, so as already mentioned, Sandy loved the demo. Yeah, Sandy loved the demo, and so do we. So I've got one. I'll see if it works. I'll just skip to this slide. So this is a part of Sandy's very large network architecture. Amazing vision, really. So at the bottom, we have all these houses, 100 million homes in the US, and all the traffic from those is being funneled up to this access network to a regional node. And these regions will be very large in this plan of maybe 100K to 1 million users. So that's a lot of traffic suddenly coming into this regional node. So it needs a very large switch. So yeah, what would that switch be like? And so I can see that I can share a screen and stop the share here. Is that right? And then, can I share a screen here?
So while Dave sets it up, this code is 20 years old, but
yeah,
was still compiled in a weekend.
Still works fine. So this is a smaller switch, obviously, just for visualization purposes. And what we've got is, I'll just slow it down a little bit. We've got packets arriving on input ports on the left, proceeding across the switch. These are switching elements with a sort of an interconnect, and then being sort of sent to their destinations, color-coded, and they appear on the right-hand side. So one of the things you can do with this little demo is you can see the logical structure of the switch. That's sort of more of a physical view. But if I just do this, then you can see that it's really got this nice sort of tree shape where the packets are, Sandy always described it as like a tree of multiplexers, multiplexing them together on the left. So what would happen is packets would arrive and they'd be buffered in the node until like a buddy turned up that was going to the same destination. And then once a buddy appeared, they would then be able to be transmitted across these 2 wires simultaneously. So you get at the outer layer, you'd have like two groups of 2, then it'd be groups of 4, and then groups of 8, then groups of 16, and then you'd end up with like a large batch going across the middle, and then demuxed on the output side. And so one of the interesting things about this is that it doesn't overload in the middle as long as I think it's non-blocking is the term. I think as long as the output ports have enough capacity, it shouldn't be dropping traffic in the middle thanks to this buffering. And I can look at various properties with this visualizer. If I just click on this and then go this, I can look at the packet delay. So one of the interesting things is that, let me see, change the flow type to be this one. There we go. Okay, so one of the interesting things is that because it groups packets together and they have to wait for a buddy to turn up, it actually works very well if there's a lot of traffic. So at very high levels of load, like at the right-hand side, the latency is very low. The worst-case delay is very low. But when the switch is lightly loaded, that's when there are some issues. But then Sandy had plans for that as well. So that's when he would have the switch detect that condition and then be able to sort of insert dummy traffic. And you can do that in this demo as well. So this thing allows you to see what happens inside the switch and get a feel for how it works and try different flow patterns and look at some stats. And this is the kind of, I really enjoyed working on this when working for Fraser Research. It was a really fun project. So that's that. I think that's all we need.
Thanks. Do you want to just get the screen share back? Thank you, David. So as you can see, a common theme of this has been that Sandy loved building demos as a vehicle for understanding and examining artifacts, and then using that to derive theoretical understanding. So the fact that we had this switch and we could mess around with it, and remember 20 years ago, this was incredibly, it's still fairly fancy, but 20 years ago, it just absolutely blew our minds. And it showed us lots and lots of different properties about how these switches go together. And this was just one of the projects that we assembled together. When we first came to Fraser Research, because Dave and I were the first two interns, we came in fresh off the boat expecting some sort of elite education in networking, and we read all the books, we were prepared. And we showed up to an empty massive office, and Sandy was there with an axe. With a saw. Yeah, not an axe. Definitely not an axe. and he loved carpentry, and we had to build an enormous table to put all the switches on. So I think it was about twice the size of this, wasn't it?
I think my contribution wasn't very.
That's right. Dave managed the process, and I was sitting there sawing away, and we built some incredible tables, and then we deployed a lot of the equipment that Alistair showed us in his talk from AT&T, recreated the old ATM networks, and then modernized them and put them together. So it's an enormous amount of learning in terms of putting together old networking kit, trying to do lots of kernel hacking and stuff, and trying to figure out exactly how we could take the next step. So as interim programs go, it was pretty amazing. And one of the things that struck with us when we were preparing to talk today was just how many of the questions that he raised are still relevant in today's research landscape. So we still don't have satisfactory end-to-end quality of service on the internet. However, we have got a partial solution to many of these things. So for example, if you use one of the big content delivery networks such as Cloudflare, they operate a huge percentage of the traffic on the internet, and they've built their own internal massively distributed systems that have proprietary technologies that do give them, as soon as you enter the Cloudflare domain, lots and lots of guarantees. Similarly, if you work with some of the big cloud providers, they have lots of elaborate systems, but they're all islands that are separated and connected via the more unreliable internet. And so some of the key questions that you could think about if you're a new student interested in getting into this space is thinking about how we can connect these islands of connectivity together. And remember, these islands can involve billions and billions of virtual machines, of physical servers with exabits of connectivity across them, but they still don't quite have a standardized mechanism of working together. And at the other end, just forgetting the big data centers is the end user. So what the project I worked on was trying to figure out if you're in a home network and you have an Ethernet TV. So this was way back 20 years ago. Now all TVs are connected. But the basic problem was how do you configure it and how do you just make these things just work without any interaction? And that in itself was a huge amount of systems work because you had to get configuration to be debuggable by a non-expert. You had to make these things just work without in the presence of lots of failure modes. And if any of you have a smart TV today, you know that it's by no means a solved problem. And if anything, it's gotten worse in those times. And also, the big ticket item, as Alistair pointed out, the big idea is, can the internet really scale in its current form to the next several orders of magnitude? If we want to drop the latency down to less than a millisecond while increasing the amount of bandwidth that we pump through this thing, these are architectural questions that are at odds with each other, and we still don't really know how to do that. We can see a way to do it using the Dave switch. I'm not sure it had a name, but how you glue all these together in the wider world remains an open question. So I'd love to continue this conversation with any students or indeed anyone who is interested in trying to bridge some of Sandy's ideas and pull those into a bigger picture. And in order to make this happen, we looked over Sandy's writings, and since Fraser Research finished in about 2010 or so, he started writing up the results of what all of the interns worked on as part of the 100 by 100 project. And the result is absolutely remarkable. It's about 118 pages. It's unfinished, yet contains the aggregation of the full stack, the full network, all the way from the low-level switches, all the way up to the architectural ideas, to the instantiation of real software and APIs that might make all this work together. And so it is our privilege in the Computer Lab to have published this as a technical report here in its unmodified form today to mark this event. And it's a hallmark of a good monograph that I started reading it just about 11 o'clock last night, and I'm pretty tired because I just kept reading it and I couldn't stop until the very end. And I've scribbled lots of notes in my copy in order to just to look into it and do a bit of extra reading and so on. But it's available as Technical Report 978. It is Sandy's last bit of work, and I cannot underline what a privilege it is for all of the interns at Fraser Research to have participated in our small way in this effort. And we look forward to continuing Sandy's ideas and trying to push his charming yet stubborn desire to have a really reliable functioning global network through the rest of our careers. So thank you very much for this opportunity to talk about it. It's like an Indian wedding. I'm just putting...
All right, we're married now. Latency management. I make no comment on that. Yeah, hi, I'm John Crowcroft. I'm from the internet, which is apparently not working. Well, obviously it is working. And so I think I'm going to just tell a bit of a story about this. So there's this contrast made between what was done by the phone companies and by the internet. And what came out of the phone companies went into what was the CCITT and the ITU, and they designed some incredibly stupid ideas for how to do data networking and collecting computers. And meanwhile, a bunch of hooligans at MIT and Berkeley, and where I was working at the time, UCL 45 years ago, started throwing together, lashing together this rubbish network out of anything we could use. And of course it didn't work very well, but it worked. And it cost virtually nothing. This was very cool. But the important thing was almost all the people involved in that came from computer science departments, and they were writing software systems, and they were thinking about the network in data and control as a computing problem, and control in particular is a distributed computing problem. And this is where Sandy's work is absolutely slap bang in the middle, and you've heard about his very early work on file systems and operating systems right the way through to network design. When you read this tech report, you'll see it's written by somebody who clearly got that this was a computer science problem, or computer engineering, if you like. I'm not going to make a distinction, that's a kind of pedantic thing to do. But understanding that we have a large-scale distributed computing problem to deal with reliability at scale, to deal with all these problems, to manage a larger number of different systems, disparate systems all around the planet, not just in the US, but everywhere. That's a really interesting thing. And so really, that ability to bridge between what was telecom engineering, what you get from the people that build wires, and then not that long through this line of work, the wireless networks, and understand what those properties that they could deliver were, but then to glue them together into an overall system. With all these ideas we've heard about, that was very cool. But also the really large-scale deployment problem had been being tackled by these hooligans building the internet. But what's really cool, the big irony, if you like, the sort of badly kept secret by the internet people, is that most of the places you look in the internet today, you look inside a data center, or you look inside a broadband access router, or you look inside a base station managing your cellular data access, or you look inside the interplanetary networking that's used, they all feature most of the ideas you've heard about that came out of the Fraser Research, all that kind of thinking. It's just not quite completely end-to-end yet, but that's because we need to get the hooligans under control a bit more, and we also need to make sure that the telecom engineers really understand this is a computer science problem. They need to understand that software systems are going to deliver this thing in the end in ways that deal with the fault tolerance at scale, that we have ways of thinking about that are somewhat different. They don't involve building a telephone switch that supports a mean time between failure of 100 years, The failure is defined as only 50% of the lines have failed, by the way. But that costs a fortune, and you can build this thing out of Raspberry Pi computers that cost 10 quid and support a few thousand users in your home. And if it goes wrong, you get another one, or another 6, or another 25, right? It's a whole different world. So that's really where I just wanted to wrap up here, that the influence of somebody who understood computer science going back 6 decades, and how that informs how you then think about the kind of ideas you hear from the telecom engineers inside AT&T, inside BT we heard about, and so on. How you put these together into a harmonious system is a massively complicated thing, and that's what we've heard. That's what this amazing man really is, the greatest contributor to that harmony. And of course, a lot of people will see him as coming from the sort of AT&T world, but a lot of people who know his work see him as coming from the computer science world. So he had to bridge those communities, and we heard about his work as a mentor in building communities that bridge that. And I think that is really all I want to say at this point. Just an extraordinary person, and an honor to have met him and had any conversation at all with for 3 seconds. So thank you very much, and back to the chair, I think, now.
Well, thank you, everybody, very much. We don't have any direct questions from people online. There are quite a lot of people joining us online, by the way. This is only a small part of the audience. So I think if anyone has any immediate questions here, we could perhaps take 1 or 2. Otherwise, we're going for refreshments outside, and you can grab the speakers of your and grill them directly. Does anyone want to raise anything here? In which case, thank you, Anil. Thank you to everybody, some of whom have come a great distance here, and thank you to all of our wonderful speakers. We've had a great range, and thank you all for joining us.
Sorry, hang on.
We
sorry.
stopped.
1 second. We stopped the recording.
It's still going.
Okay. I made a big mistake. Not an uncommon thing, but we are delighted that Elizabeth is going to say 1 or 2 last words to round off, which I foolishly forgot. Elizabeth, over to you.
Okay, thank you. So thank you all. My first thing I wanted just to say was thank you to all the people that have organized today, Anil, everybody. The work that Dave put in to rework the Switch demo, all of it. It's been a wonderful tribute for Sandy, and our entire family are very appreciative. Not only to the people here, but to the institution that put this together, to your work with the report, which I really appreciate. And it seemed to me, that I'm not sure that when Sandy came to do the diploma course back when, that he had any idea the impact that was going to have on his career, because it did. It was a real foundation stone for setting him up, for allowing him to enact the ideas that he had. But more than that, it established a strong connection with this institution, for which he had immense regard throughout his life, not only for the people that were here, but for the work that is done here. And he really looked forward to the times that he came here to interact with faculty. He would have conversations with Maurice Wilkes and David Wheeler and many of the people here. But as has been said, he also wanted to talk to the very newest graduate student. he would say to me that he wasn't a good teacher. I don't think he had any idea of the impact that he had on the people that he worked with, the people that he mentored. He just didn't. But it's very clear from what's been said today, but also the notes and comments that I've had in the last year, that was a real impact that he had on people. Excuse me. His enjoyment of coming here, which he did a lot, particularly when we were working on the Fraser Research Project, I would come as well, and so I got to know people. But in with that, I would be remiss if I didn't recognize one particular person, and that's you, Andy. And the discussions that you had with him, it seemed to me that the two of you never had enough time to finish your conversations. There was always something else that sort of came up, but that meant a great deal to him, those conversations. The support that you gave him over the years for his ideas and his projects, all sorts of them. I found a letter that you wrote in support of something. But more than that, more than all of that, I think on his behalf, I would like to thank you for your friendship. I think that meant a great deal to him. He would never have said so, but it was there. And so finally, I just, on behalf of our entire family, Sandy's family, my side of the family, all of us, the honor that you've done for Sandy in doing this today. It means a great deal to us. We will have the video for the family for forever. So thank you so much.